Have you ever wondered if light can behave like a particle? Can particles behave like waves? The answer to this question led Louis de Broglie to a groundbreaking equation in 1924, one that revolutionized our understanding of the quantum world. Proposing a radical theory, Louis de Broglie suggested that particles, much like light, exhibit both wave and particle properties. To underline this duality, he introduced an equation now famously known as de Broglie's equation. This equation elegantly ties the familiar world of classical physics with the strange, counterintuitive realm of quantum mechanics. De Broglie's equation is quite simple. It states that the wavelength of a particle is equal to Planck's constant, denoted by h, divided by the product of the particle's mass and its velocity. In mathematical form, it's expressed as mv. Here, lambda represents the wavelength, m stands for mass, and v denotes velocity. Now, why is this equation significant? Well, it tells us that every particle has a wavelength. In other words, every particle, from a tiny electron to an enormous planet, behaves like a wave. The faster a particle moves or the more massive it is, the shorter its wavelength. Conversely, the slower a particle moves or the less massive it is, the longer its wavelength. To make this idea more palatable, imagine a small boat and a large ship moving at the same speed in the ocean. The ship, being more massive, creates shorter, choppier waves, while the boat, being less massive, creates longer, smoother waves. This is a rough analogy, but it gives you a sense of the principle behind de Broglie's equation. Remember, de Broglie's equation is not just a fascinating theoretical concept. It's a fundamental part of quantum mechanics with far-reaching implications in fields ranging from chemistry to electronics and even computer science. It's a testament to the beauty of physics, showing us that the universe is more interconnected and complex than we could ever imagine. So, what have we gathered about de Broglie's equation? Firstly, it introduces the wave-particle duality concept, stating that all particles, regardless of their size or speed, have a wavelength. Secondly, the equation is simple yet profound. It connects the wavelength of a particle to its mass and velocity, using Planck's constant. Lastly, it's a cornerstone of quantum mechanics, with applications in various scientific fields. Understanding de Broglie's equation is like holding a key to the quantum world. It's a reminder that in the realm of the very small, everyday intuition may not apply, and particles can behave in ways that seem downright bizarre. But that's the beauty of quantum mechanics, and de Broglie's equation is one of its most elegant expressions.